Hello viewers and welcome to another episode of Space Science with Python. Last time and the sessions before we were talking a lot about state vectors, about positional vectors and velocity vectors, where we computed the position of the Earth as seen from the Sun. We determined the movement of the solar system barycenter with respect to the Sun and also with respect to the phase angles of the planets. And in the next sessions we will cover also the appearances of the planets and objects as seen from Earth, because at the end of the day we need a telescope somewhere on our home planet or some telescope in space like the Hubble Space Telescope or the upcoming James Webb Telescope. And what we see is of course not some kind of three-dimensional image, but more like a projection in the sky. And this projection is covered by a coordinate system. And to make or to handle this and imagine this more easier than just by computing some numbers, I would like to introduce a Planetarium software today that we will cover, where we cover the basics today, and then next time we will cover the sky coordinates. And this software is called Stellarium. And Stellarium, as you can see here, the link is in the description, is an open source toolkit that you can download for all operating systems, Linux, Mac, Windows, whatsoever. There is even, I think, also an iOS and even an Android application that you can download. And here on the computer, it's open source and it can be used for free. And it's extremely sophisticated, so it's very, very complex. And today I will give you a short introduction into the software, how to use it, how to interpret some things. But again, the topic sky coordinates, coordinate systems, and so on, and appearances in the sky will be covered in the next video, because this is like a new scientific field where we will use also Python again to compute these values and compare them with Stellarium. Now, I already started it, and as you can see here, this is the Planetarium software. And what do we see? Now, well, first of all, it's apparently this is the night sky, and we have here some ground with the directions south, east, west, southwest, and so on. So we can rotate here by 360 degrees, and of course the position or the sky and the night sky appearance is of course determined by the time, but also by the location where we are. And if you take a look on the left, you see that the position is now Stuttgart, so basically the city where I'm currently sitting at 0 meters. Well, it's not 100% true. Actually, I'm somewhere around 400 meters or so, but this checks out. Now, Stellarium has like two setting bars that are disappearing here all the time. On the left side we have the some configuration settings and so on, and on the bottom we have some settings for the appearance here in the Planetarium software. The upper right has also some things for the amateur astronomers, where you can adjust or take a look how the sky or a part of the sky will look like with your camera, with a telescope, with your binoculars or whatsoever. But we will not cover this topic. We will just cover the basics of the tools that are provided here on the bottom left and on the left. So let's orientate a little bit first. So now it's almost 9:30 in the evening. Not UTC, but local time. So this is now the actual appearance. And if I look out of the window, well, there is a moon shining, and there are two bright stars. And these bright stars are not really stars, but they are actually Jupiter and Saturn. So if you are wondering currently, now in mid of October, what kind of bright star this is, that it's coming out of the horizon in the early evening, it's actually Jupiter. So it's currently moving up, and you can observe it nicely with your naked eyes. But even with binoculars, you can see also the moons that have been discovered by Galileo Galilei. Now let's orientate a little bit first. On the left side, we have our location window setting, where we can adjust the settings for our location. So now you see the red arrow indicates the southern Germany, but we can choose another city or just click around And let's go a little bit to the south, to the equator, and then you see how the sky, how the appearance changes a little bit. So let's take Jupiter, Saturn, and the Moon as a reference, and we are moving now our arrow a little bit more down, and then you see for this in the same time they are moving a little bit up, so the whole appearance is totally different. And also in the southern hemisphere we see also other stars that cannot be observed in the northern hemisphere, and we will get back to this and compute also all these features in the future. But now let's go back to Stuttgart. Hopefully it finds it. Well, apparently not. Now this is really bad, but I think I can get information somewhere here. Maybe from Germany, or maybe it's even, if I just pirate Europe, I can just scroll to S. I don't know, probably the search engine is not really working for some strange reason. Oh, ST, there it is. Yeah, somehow it didn't find it. Anyway, so we are back in Stuttgart now. We can adjust the time either here with this window, and then we can adjust the date and also the times, or here on the bottom by fast forwarding the time. And we'll take a look at this also later, what happens. So let's not change here. We have also some other settings. Again, this is like you have to explore a lot. You cannot damage anything, don't worry. Where we, for example, can adjust some settings. We can adjust the projection. Do we want to have a fisheye projection or whatsoever? We stick now with this so-called stereographic projection. So this is just other ways of displaying the sky on our screen. We can set also a so-called limiting magnitude. So if you are in the city, the limiting magnitude decreases, which means the number gets smaller, and a small magnitude means a brighter star. So the point is, in the city, due to the light pollution, you do not see the fainter stars, so they just vanish, they disappear from for you. And if you go somewhere else, for example in the desert, for example, the limiting magnitude is of course higher, so the magnitude is a larger number and you see fainter stars. Now there's also other settings here where we can adjust some scales, where we can also show the orbits of planets. Now this is also quite interesting. If you recall the reference frame I explained the other day, the ecliptic J2000, you may remember that our Earth is moving on the so-called ecliptic plane, or the ecliptic plane is defined by the movement of the Earth around the Sun, and all other planets are almost very close to the ecliptic plane, the major planets. So if we now plot the orbits of the planets, they will more or less follow a straight line or a line across the sky, and the individual lines show only minor deviations. So let's have a look. And there you see, for example, the orbits, the projected orbits of all the planets, Jupiter, Saturn, and of course also the other planets, Uranus, and also Mars is probably here, and also Venus, that are currently under the horizon. And for Jupiter, you see this also quite crowded because all the moons are drawn in here as well. But let's get rid of the orbits. We have also deep sky catalogs where you can add all the deep sky objects like galaxies, nebula, and so on. There are also a lot of things for markings. So markings, you see there are a lot of grids here: equatorial grid, ecliptic grid. Well, this is like the ecliptic J2000, azimuthal grid, a galactical, supergalactic, and so on. So it's really overwhelming what we see here. And if you click, for example, on an object like, let's take the moon, you see also a lot of parameters on the left side that correspond to this coordinate systems. You see here the galactic coordinates, the supergalactic coordinates, ecliptic longitude, and so on. But don't be too confused. We will get to this topic coordinate system in another video, in the next one. We will also use Spice and Python to compute these parameters and try to understand it more deeply. For now, I think it's quite overwhelming enough to understand what we see here today. But let's get back to this in a moment. Now, we can also change the landscape, so a little bit the settings, whether we are here on the ocean or even Saturn. So just play around. Saturn is also quite nice because you see then the ring in the sky, so a projection, which is also pretty amazing, and other settings. And then we have a search window, of course, configuration as well. I mean, yeah, just try it out. It's not really, it's a very fast tool, and here you see the displayed field. So when I click on the moon, all the information can be adjusted here. So we do the adjustments also later in the other video to sort these things a little bit out. And then finally, we can also perform some astronomical calculations. So basically what we do with Spice and Python is shown here, where you can compute the ephemeris, positions of objects and coordinates and so on. And what the tool does here in the front end, we do this in the back end, right? So we use Python and Spice to compute these values and understand how this is being computed. Here, it's of course nice to see these values, but you don't know where they come from. And thanks to Python and so on, we really know how to do it. And I think this is pretty amazing. But yeah, and it can be used to compare also results. So we have here position, ephemeris, transits, and other phenomena. So very extensive. Now let's orientate a little bit in the night sky before we go to the stars and also the constellations. Let's take a look at the moon. So a lot of things are being simulated. I just pressed the space bar to center the moon, and let's zoom in there, and we see that also the phases of the moon are displayed correctly. So it's almost full moon, almost. So if we change the date a little bit, so let's say we go a few days back, you see it's getting darker, the phase changes. So this is quite realistic simulation of all effects, all appearances in the night sky. So this is pretty amazing. But let's take the current date. The same thing applies also for the planets. So if we go, for example, to Jupiter, we center it, we zoom in there, then we see also the Galilean moons, Callisto, Io, Ganymede, and Europa. And if we fast forward it, we will see the movement of the moons. But this will look a little bit chaotic. So you will see when we have centered Jupiter, and if we fast forward it, you will see that the sky apparently is rotating. The object goes down below the horizon, and if you want to see the movement of the moons, well, the perspective changes. It goes under the horizon. This is not really user friendly, but we can adjust things. So let's go back in time. Yeah, we can remove the cardinal points, so south, west, east, and so on. We remove the atmosphere, so everything becomes clear, and we remove the ground. So this is now the entire night sky. It's quite confusing, I know. So the sun is below the horizon, but now we see the sun because I just removed the horizon, right? There we see also Venus, we see Mars, Mercury, and so on. And if I now fast forward in time, we still see this rotation because the camera is still adjusted to my view of the horizon. So if I just paste things up, it gets really confusing. It makes this sinus movement, and it's, can be quite confusing in the head, right? But this is also not a problem, because let's go back in time. So now let's add the ground again and also the atmosphere a little bit, because the Earth is of course rotating, and of course apparently the sky rotates above us. And well, if we want to compensate for this, we can switch to another, let's say, virtual telescope mount, which is called the so-called equatorial mount. So what does it mean? That means that the axis of our rotation is aligned with the axis of our home planet. So we are rotating with the night sky, and we don't see the sinus movement anymore. Everything is steady, and we are moving with the night sky. Maybe you have seen this kind of time-lapse movies where people are not creating time-lapse movies of the Milky Way, how it comes out of the horizon or so, but they are really following the horizon, and not the horizon, they are following the Milky Way or planets, and the ground below them is moving away or rotating. I will add a link into the description to some YouTube video of some time-lapse videos where you will see this. Then you will know what I mean. Now, so we can now click here again on Jupiter, readjust the time. We go a little bit closer, okay? And now we can switch to the equatorial mount. And the question is, where does the axis point? So before we do it, let's see where is the axis pointing. And the axis is pointing towards the so-called equatorial North Pole. And there is one particular star that is very close to this North Pole, and this star is called Polaris. Now, Polaris can be found in the north, so we are here in the south. Let's rotate a little bit. And where do we find it? Well, we can turn on our constellation lines to support us a little bit, and there we see Ursa Major, the bear. And maybe you have seen it if you live in the northern hemisphere. I'm sorry for all viewers from the southern hemisphere. We see these 3 particular stars and these 4 ones, creating the so-called Big Dipper. And this constellation, you have probably seen it, right? It's very apparent in the night sky. And if you take the last 2 stars, so this one here and this one here, and you have this imaginary line, and you extend this line by, I think, a factor of 5, you reach to the star Polaris, and Polaris is here. So you see here Polaris as part of Ursa Minor. And now if we rotate the night sky, we will see that everything rotates around the star. Well, not actually the star, but it's very close to this rotation axis, so it appears that everything is rotating around Polaris. So let's move a bit faster, and you see the night sky is now rotating, and this star is staying in the center. So everything is revolving around this, yeah, they call it imaginary North Pole. So I think this is quite impressive. You see the Big Dipper is moving also here anti-clockwise, but the pointing is still correct, pointing towards Polaris all the time. And now our telescope, if we change the switch, now the sun rises, excuse me. If we switch now to the equatorial mount, then our rotation axis of our camera will be adjusted with this point, or with this point and the south point, so the South Pole. So let's go back to Jupiter. Click here, clicking spacebar, zooming in, turning off the constellations, and now switching to the equatorial mount. We see that there's a small switch here a little bit. And now if we we pressed enter the spacebar, so we are still focusing or centralizing Jupiter. And if you go, for example, now back in time, maybe, we see that now the ground is moving a little bit away, and we are tracking the stars, we are tracking the planet here. Of course, not the planet per se, because the planet is, of course, moving against the star background. So the star, yeah, it's steady state. Of course, this is also not 100% true, but let's say this is steady state. And Jupiter is, of course, a little bit moving, but yeah, for a few hours, this is fine. Now let's see, everything rotates with it. So that's quite nice. Now we can turn off the ground and turn off the atmosphere, and now we can zoom in into Jupiter, and we will see that there will be no wobbling around. We see that, yeah, now the time is running quite quickly. You see here the minutes. It's now an hour is only a few seconds. And you see the rotation of Jupiter and the moons, how they move. So now, for example, here at 1:30 UTC, so no, not UTC, and it's UTC plus 2, so UTC would be half an hour before midnight. The moon Ganymede should move in front of Jupiter. So you see the small Ganymede, yeah, not covering, but partially covering Jupiter, and then leaving Jupiter a few minutes later, or a few hours. And this is how it looks like, the movement of the moons around Jupiter. And this movement, this particular movement, made Galileo quite suspicious, because the movement didn't fit with the idea of a geocentric understanding that the Earth is in the center of the universe, or of the solar system. This didn't fit, right? Because this would be try to explain the movement of these moons orbiting our home planet. It had to be that the moons are revolving around Jupiter, and Galileo was right. So you see the movement of the moons, and then if you go even faster in time, I should turn off also the cardinal points. If we move even faster, you see the movement of the moon. So one revolution is like around 28 days or 30 days. And if you go a little bit faster, so take a look at the clock, you see that also the other planet starts to move, because now it's getting really fast. Yeah, the moon is moving around, coming very close to Venus also, coming again close to Jupiter, creating a nice image for photos. And then you can go even faster and faster, and you see how it slowly moves. So Jupiter is moving, the sun is moving. Okay, apparently the sun is not moving, but apparently the sun is moving, right? And then we see also Mars and Jupiter. Oh, this is also a nice picture here. Next year, we go back in time. You can take a look, Mars and Jupiter coming very close together. So this should be a very nice picture for the astrophotographers. So pretty nice. The red Mars with Jupiter and its moons. So yeah, this is how the movement looks like, and it gets even worse. So let's focus maybe a star like Betelgeuse of the Orion constellation. Let's go to the current date. Orion, you've seen it probably, right? The 3 stars here, the Orion Nebula, and the stars, and with their different colors. And now let's do something really wild. We are now going into the future, but even faster, way faster, even way faster for years, or even more faster. And even now with this velocity, you see that the night sky is a little bit moving. You see, how can this happen? Because we said that everything should be fixed. Well, even our Earth, the rotation axis of the Earth, has a small so-called precession. So it's the rotation axis of the Earth is a little bit, let's say, wobbly. So it's not steady state. And another thing happens. The stars have a movement, and this movement can also be seen or even simulated in Stellarium. So now let's take a look at some stars. We are now making it now even faster and faster. Now you see the rotation of the sun, of the Earth. It's the rotation axis is making the night sky a little bit wobbly. And here you see some stars, Rigil Centaurus, for example, another star. And look how they move. They are moving quite fast. Arcturus and Spica, they are even overtaking somehow. So this is really impressive that even the stars, or some close stars, have such high velocity. And now it finishes at the year 100,000. So this is the end of the simulation. Stellarium has no more data for this. And let's take a look at the constellations. And the constellations now, let's activate the ground and the atmosphere. The constellations, they are completely damaged. So I don't see anything familiar. Let's create the cardinal points. Let's go to the north. Ursa Major. Could be this one here. Maybe it was once Ursa Major. So as you see, even the night sky is not preserved for an eternity. It's changing. And it looks a little bit horrible, right? So let's go back into our today's state, and everything is fine again. So this is quite impressive what you can simulate with Stellarium. So this is really, really cool, I would say. Yeah, so let's go here also a little bit the other settings. We have also now our grids, like for example the ecliptic grid, as I introduced it last time. Don't be bothered by all this degrees and this grid and so on. I will explain this next time. We will have a deep dive into sky coordinates in this topic because this is really confusing and it really needs some time to explain it properly. You can also activate the deep sky objects to see where is everything. For example, you've heard about the Andromeda galaxy. Where is the Andromeda galaxy actually? And if you take the constellation lines, you can orientate a little bit where the Andromeda galaxy is. So you can here center it, zoom in, and then you see there is the Andromeda galaxy that is currently approaching us. So the Milky Way and the Andromeda galaxy are on a collision course, but don't worry, this will take millions or billions of years. Now we can also turn on and off the planet labels, of course. Another interesting feature is the so-called night mode. So I will switch now to the night mode and you will see something strange. Everything becomes red. And this is especially good for amateur astronomers who are doing some visual observations, because the eye adapts to the darkness, and it takes like around in average 20 to 30 minutes. So if you go from a bright room outside while it's night, you won't see anything at all, right? Especially if there are no traffic, if there are no lights or lamps or whatsoever. But over time, you will recognize that you see better and better in the night or in the darkness. And this has several effects with the eye. Don't want to go too deep into this. But if you want to, for example, work with the Planetarium software while you are doing some visual observations, you can or you should switch to a red light, because the red light is affecting the eye, or let's say the so-called night adaptation, less severely than blue light or even bright white light or whatsoever. So the right light is being used by amateur astronomers to keep their this adaptation, to still see everything in the dark, but also to be able to work with software, or also with the literature or with their maps. So they also have red light lamps to read, for example, sky maps and so on. But let's turn it off. We can also compute the angle measures between two objects. We'll get also to this next time. You can also show the exoplanets. Of course, we don't see them, but you can indicate the positions. We can toggle the meteor showers. So where are currently some meteor showers? Meteor shower will also be a big topic in our Python tutorials. So I hope you look forward to this. Meteors are really one of my favorite topics. It's really amazing and impressive. And also artificial satellites, where you can also take a look where the ISS is passing by, but also this passage flight times. We will get back to this as well. So as you can see, a lot of things to cover. I always say, next time, or in the future. But it's a very complex and vast topic, a huge domain where we can compute literally anything. Now, again, if we go back to our moon and all the settings here, I would recommend you to go a little bit through it and take a look, right? I mean, some are, let's say, self-explanatory, but only a few, right? Like, for example, illumination percentage. Well, the moon is currently 96.7% illuminated. The distance from the sun is surprisingly almost 1 AU. The distance to us, it's also given in AU. It's quite counterintuitive. Here's beta. It's now 390,000 kilometers or around. We have like also the orbital velocity in kilometers per second, heliocentric velocity, so the velocity of the moon revolving around the sun, currently around 30 kilometers per second. The apparent diameter, so what is the diameter of the moon in the sky? So only half a degree, so this is like 0 degrees. This is now the arc minutes, and 60 arc minutes are 1 degree. And here you have the arc seconds, so 60 arc seconds are 1 arc minute. And some physical parameters like the diameter of the moon, and other parameters like also the albedo, so the percentage of the light that is being reflected. And again, here you see the magnitude, the brightness. We will compute this. We will compute the coordinate systems and distinguish between this RA DEC and this IZ alt and galactic long lat and whatsoever. So don't be confused by all these moving numbers. We will compute them next time. Okay, this was the quick introduction to Stellarium. We will use Stellarium frequently, especially when we are computing sky coordinates, positions in the sky, or when we are trying to compute phenomena in the sky, because at the end of the day, as an observer on the Earth, we are observing the sky and we would like to see where is a certain planet, where are the asteroids, where do meteors appear, or when is it visible. So there are a lot of questions to answer, and of course it's really helpful to have something to visualize it, so we can stick with Python and printing commands and results. But in the long run, this is really confusing, and it gives no idea what these numbers mean. And such a nice Planetarium software allows you, first of all, to learn a little bit about the night sky, and also to verify your results or to understand the results. What are we computing? I hope you enjoyed today's video. It was just a small introduction into Stellarium. Try it out, play around, take a look at the Southern Hemisphere, or if you're living in Australia, take a look at the Northern Hemisphere. And next time we will get back to Python, compute positions, and compare it with the software here. And until then, take care and see you next time.